Welcome to this lecture in the ongoing series of lectures in real analysis. Today we'll be looking at yet another reformulation of the notion of continuity in the form of a theorem, of course, even though the title features a definition. Last time we looked at the notion of a reformulation of the notion of continuity in terms of neighborhoods, pre-images of neighborhoods, etc. Let me not get into the details of what it was. Basically, the philosophy was exactly as it has been in the all previous lectures, that sufficiently nearby points go to nearby points. So far we have seen three different quote-unquote definitions of continuity. The first was the geometric definition, or what I call the geometric definition, which is something that you would not find in textbooks as such. And then we showed that the epsilon delta definition and the definition via neighborhoods are equivalent to it. We proved all those things. And let me just recall one special case, is that suppose we have a globally continuous function. By that I mean that it is continuous at every point of its domain. Then this is same as saying that the pre-image of any open set in R is the intersection of an open set in R with the domain of F. So that's a very neat reformulation of global continuity. Anyway, these are the problems. And now let us look at the material of this lecture. So we start with a function on a subset S of R, and we fix a point on we fix a point in the domain of the function, and then we show that the following are equivalent. And what are the following? The first is that F is continuous at x naught. And the second is that whenever, and this looks a little bit wordy, but it's something very simple. Whenever xn is a sequence such that all of its points are in the domain of the function and it converges to x naught as n approaches infinity, then let me write if rather than whenever, it looks better. If xn is a sequence such that blah blah blah, then the image sequence converges and its limit is fx naught. So it is still saying that sufficiently nearby points are mapping to nearby points in a somewhat not so obvious way, but if you just think about it, what it is saying is that if some sequence of points gets closer and closer to x naught, and of course this sequence of points is in the domain of the function, then its image also gets closer and closer to the image corresponding to the point x naught. So it's basically saying the same thing as we've been saying all the while, but we have to prove this. This statement and this statement are on the face of it different, so we have to prove this. And to prove this, I'll use the notion of epsilon delta continuity. That's what I will use as one, because we have shown that is same as saying this. Continuity at x naught is same as the epsilon delta condition being satisfied at x naught. Anyway, so here is the proof. And as always, one should understand this proof in terms of pictures, and I'll try to draw the pictures as I go along. So that means that we are assuming 1. Assume 1. And we want to show 2. So let xn be some sequence. So a sequence such that xn is an S for all n, and xn converges to x naught. Then we want to show that, let me write that in yellow. We want to show this. This is our goal. So this is of course saying two things. One is that this sequence, the image sequence is convergent, and the limit is this. So that is conveniently written in a shorthand. Alright, so how do we show something is convergent? We fix an epsilon and then we find a large enough n. So let epsilon greater than 0 be fixed, be arbitrary. And now by 1, and by using the epsilon delta criterion, there is delta greater than 0 such that such that whenever x is chosen in S and x is not very far away from less than delta far away from x naught, we have fx is less than epsilon far away from fx naught. So let me draw a picture. We have seen this picture multiple times, but let me draw it. So let's say this is, or maybe this is x naught, and this is x naught plus delta, this is x naught minus delta, and here is, let's say, fx naught, and extend this. So okay, maybe I should use a different color. This is epsilon, bad, this is epsilon. Alright, and what this is saying is that the graph of the function, if you just focus on this much, again this should be dotted, if you just focus on, sorry, so the graph is something like this. It is whenever you are within this region, the image is between these epsilon bounds about the point of x naught. So that's how the graph looks like. So if whatever sequence that we have fixed, this sequence, eventually it is going to fall inside this region, meaning all the points of the sequence eventually, ultimately, will be here. That's what it means to say that xn converges to x naught. So all of those things which are inside, all the points of the sequence which are inside this region, will be mapped within epsilon of fx naught, because that's how the graph is behaving. So for large enough values of little n, we see that fx, f of xn is within epsilon distance of fx naught. And that's exactly what we wanted to prove. So let me write that down. Okay, so since xn converges to x naught, there is some n such that whenever such that xn minus x naught is less than delta, whenever n is larger than capital N. It's immediate from the definition of convergence, and therefore f of xn minus f of x naught is less than epsilon whenever n is greater than equal to n. So whenever n is greater than equal to n, this condition is satisfied. Each xn is already in the domain. So by this statement, we see that this follows. And since epsilon was arbitrary, this means that the yellow statement has been proven, because for each epsilon we are able to find a large enough n for which this statement folds. So since epsilon was arbitrary, we see that f of xn converges to f of x naught. So this was very straightforward. The converse is also not very difficult, but it is a little bit more interesting. The proof, I mean. So of course here we'll assume 2 and we'll go by contradiction, although I think it's not necessary to go by contradiction, but it's most convenient. So assume that f is not continuous at x naught. So that means then there is epsilon greater than 0 such that no delta works. No delta works. What does that mean? That is, for each n greater than equal to 1, there is a point xn in S which is at most, or rather less than 1 by n distance away from x naught, such that f of xn minus f of x naught is greater than epsilon. So this is, I mean, one should realize that this is precisely the contrapositive of continuity. Well, I shouldn't say contrapositive. This is precisely the opposite of f being continuous at x naught. And we have assumed that f is not continuous at x naught, so this is what it means. And, you know, you should spend time. If this is not immediately clear, then you should spend time and figure this out. The why this is the same thing as saying, or why at least this is an implication of f not being continuous at x naught. Okay. So now what we have developed is that we have developed a sequence. So thus xn is a sequence such that xn is an S for all n and xn converges to x naught. Why is that? Because the distance of xn with x naught is at most 1 by n, so therefore xn converges to x naught. So therefore by 2, by statement 2 we have, let me show you the statement 2 issue. This is statement 2. We have fxn converges to fx naught. But what does that mean? And hence there is n large enough such that fxn minus fx naught absolute value is less than epsilon whenever n exceeds capital N, which is in contradiction with the first statement. So let me mark this as star. Which contradicts star. Star was for each natural number and this is for large enough natural numbers, and therefore we have a contradiction. This contradiction proves the required thing. So let me not write all that. Let me just add the Helmholtz symbol. Yeah. So very simple. I mean, there is nothing complicated going on. And this is our last reformulation of continuity. Next time we'll, look at other things rather than just reformulating continuity. We have 4 different ways of looking at continuity, and in proving some statements, some formulation may be easier to apply. So that's something to keep in mind. And now let me leave you with a few very simple exercises so that you have practice. So the first exercise is using this formalism via sequences of continuity, prove the following. So the first is the identity map. Is continuous. So what does the identity map do? It takes x to x. That's what the identity map does. I'm sure I've given this as an exercise in some previous lecture. Another thing is, let S be a subset of R, non-empty. Then the inclusion map. Is continuous. This is a more general statement than the one above. And again, I've already given this as an exercise before, I'm sure. Why is this a special case of the one above? Because if you just substitute S equals R, then you precisely recover this statement. The inclusion. So what is the inclusion map? It just takes little x to x. That's the inclusion map. Lastly, another, in fact, this thing is an exercise in the problems above in this particular lecture. So the absolute value function is continuous. So very simple exercises. Please use this notion just to get some practice. Use this criterion of continuity. In fact, you're welcome to use prove these three statements with all the four notions, but for this lecture I want you to just focus on the one using convergence. Anyway, enough about reformulating continuity. As usual, like, comment, share, subscribe. I also have Patreon. The link is in the description below. Thank you for listening, and I will see you next time.